All right, well, good Monday morning. Welcome to another fun-filled day of calculus. The plan today is just to keep talking derivatives. We're going to talk a little bit what we use them for, and then I'm going to introduce you to one more rule, which will take care of function composition, and we'll pretty much be ready to differentiate anything that comes our way. We have a few specific types of functions like exponentials and logs and things like that we're going to have to derive, but we'll get those along the way. So that's our plan for today. But before we go into that, I know that there is homework due tonight, and I imagine there might be a few that people want to look at. So let's start there. There's some homework questions we want to address before moving on.
I have one. Could you do 3.3 question 8?
3.3 number 8. All right, that's on the list there, Tim. Any others? Okay, well then let's go see if we can take care of that one. So I'll go ahead and share my screen, and then we'll go see what that looks like. All right, waiting for this one to warm up and load. Here's your bad joke of the day. So it's a two-parter, so attention. Why did the chicken cross the road? Well, to get to your house. Okay, knock, knock. This is when you say who's there.
Who's there?
Thanks. The chicken, duh.
Chicken who?
No, that was the joke, right? Why'd the chicken cross the road? To get to your house. Knock, knock, who's there? The chicken. I told you it was a bad joke. All right, clearly too much for this early in the morning. All right, so enough wasting our time. So does this look right, Tim, or at least something similar to this? Where we've got f of x is 4x to the fifth plus 4x to the fourth plus 2x cubed all over x to the fourth. And we want to find f prime.
Yeah.
Okay. So basically, this is exactly what it looks like. It just says, let's differentiate this function. All right, so what do you think? What rule do you want to use? What rules, or how do you want to attack this?
The power rule and then the quotient rule.
Okay, so quotient rule, since we've got division, you can clearly see the division, right? We got that big bar right here. So there's definitely division, which suggests that we can use a quotient rule. And within the quotient rule, we're definitely going to use power rules, right? So I think that's a perfectly fine place to start. Let me go ahead and share the whiteboard here, and then we'll see where this goes. And Ali, I did see your question about number 7 from 3.5. We can definitely address that next. Okay, so let's just start here with the whiteboard. And so here's our function. We've got f of x equals, let's get it over here. So f of x is 4x to the fifth plus 4x to the fourth plus 2x cubed over x to the fourth. Okay, so if we're going to use the quotient rule, remember how we do this. We need the function's derivatives from the function on top and the one on the bottom. So let me go ahead and just kind of set this up the way that I always do. So there's my function on top. Here's my function that's going to be on the bottom, and then I need their derivatives. Okay, so we'll start with the bottom one because it's a little bit easier. Since it's just x to the fourth, we're going to use the power rule. So how's the power rule work? What's this one going to give us?
4x cubed.
Good, 4x cubed. That power comes out front as a multiple, and then we decrease the exponent by 1. That's always the case. We proved that using the limit definition last week, so we know that we can always do that. All right, so there's the derivative of that one. Now we're going to come here to the one on top and do the same thing. Now, these also have the power, so we're using the power rules, but they also have constant multiples. And the constant multiples, they stick around. They show up in the derivative. So like this one, 4x to the fifth, we're going to get 4 times 5x to the fourth. The 5x to the fourth is the x to the fifth power rule. That 5 comes out front as a multiple, decrease the power by 1. But the 4 out front stays there. Constant multiples stick around. So the 4x to the fourth is going to give us 4 times 4x cubed. Again, the constant 4 stays there. The x to the fourth, 4 comes out front, decrease exponent by 1. And then we're going to get 2 times 3x squared. The 2 is the 2, x cubed is derivative is 3x squared. So I'm going to go ahead and just distribute those to make life a little bit nicer. But there's the derivative of the top function. Now, some of you may be getting to the point where you don't need to write out these intermediate steps and you just go, oh, I'm going to take 5 times 4, decrease by 1. 4 times 4, decrease by 1. 3 times 2, decrease by 1. That's where I am, but obviously I've been doing calculus a long time. But it can get pretty fast, actually, if we're in this sort of situation. All right, so now let's set up using the quotient rule what this is going to look like. All right, so there's that little rhymey thing that I never remember. So I'll just use my little trick here. I want to multiply one times the other. I'll use the positive slope one to tell me that that's going to be a positive. So that's going to be the positive piece up here. So we get 20x to the fourth plus 16x cubed plus 6x squared. All of that times x to the fourth. So it's the derivative of the top times the bottom. Then we're going to subtract 4x cubed times 4x to the fifth plus 4x to the fourth plus 2x cubed. So that's the derivative of the bottom times the top. So that's always what this looks like on top. And then on the bottom, you just take this guy x to the fourth, and we square it. So that little rhyming thing, it goes low d high minus high d low, square the bottom, and away you go. All right, well, there's the quotient rule.
I think that's where I made a mistake. I squared the the derivative of the bottom.
That would definitely do it, because that's going to change things completely, right? X to the 4 squared compared to 4x cubed squared. Weird things happen. So now, of course, we probably want to try to simplify this a bit, right? Distribute group-like terms, try to divide. And this actually will simplify a lot. But I think I'm just going to leave it here for right now. I'll let you do that as an algebra exercise. However, I do want to show you a faster way of doing this one. And this guy is actually faster because you don't actually have to do the quotient rule. And if I could see your faces, this is probably when some of you would perk up your ears a bit and be like, wait, what? No quotient rule. But we're dividing. How do we not do quotient rule if we're dividing? Well, here's what we could have done at the start. We could have done a little bit of an algebra step, that would have saved us a lot of time when it comes to the calculus. Since I'm dividing by just one term, just dividing by x to the fourth, I can actually split this apart into 3 pieces, each of them with a divided by x to the fourth. And watch what happens. Now this simplifies, right? X to the fifth over x to the fourth is the same as x. That's just 4x. The second one, the x to the fourths cancel, so that's the same as 4. And this one, x cubed over x to the fourth, leaves me an x on the bottom. So algebraic step brings us to this function. And this one's really easy to differentiate, especially if we recognize that that 2 over x is the same as 2 times x to the minus 1. Because now if we differentiate 4x, well, the 4 stays there. The derivative of x is 1, so I get just 4. This plus 4 goes away, right? Since it's a constant being added, it goes to 0. And then 2x to the minus 1 becomes minus 2 x to the minus 2. So this is the derivative, 4 minus 2x squared. And I promise you that if you do all of the algebra on this thing, it's going to turn into 4 minus 2x squared. Okay, so Leah, when you said which rule did I use to start that second part? You mean when I wrote this step right here where I split it apart? Below the squiggle, yeah, okay. So this right here, I wouldn't say that it's a rule. It's just, this is how fractions work. If you have a common denominator and you add the fractions together, then it's the same as adding the pieces on top. Right? That was the whole adding fractions with common denominator thing. Well, I just did that in reverse. I split this one big fraction up into 3 smaller pieces. So I guess if you want to attach a name to it, it's the rule of fraction addition, maybe. So this happens, or this can save you a lot of time. And to recognize it, the key to recognizing it is that, or that you can use it, is the fact that we are dividing by just a single term on the bottom. This was just x to the fourth. It wasn't like x to the fourth plus 2 or x minus 5 or something like that. If you have just a single term on the bottom, you can always split it up like this. Had this been flipped over, let's say it had been x to the fourth over all this other stuff, then we would have had to use the quotient rule because it wouldn't have split up because of the fact that there was addition then on the bottom. All right, so this is one of those places where algebra is your friend. Like if you think about it, we have to do some algebra and then calculus if we do it the second way. The first way, we have to do some calculus and then some algebra. So we're still doing both. It's just by doing the algebra first, we made the calculus much easier. And the algebra itself was pretty simple. So just watch out for that. It can be really useful. And avoiding the quotient rule is always huge. Because as I'm sure you guys have noticed, there are lots of places where you can make an error with the quotient rule since there's lots of steps. So the more you can avoid that, the better. All right, so how do we feel about this one? Good?
Better, yeah.
Better? I'll take better. Okay, so Aaliyah, then you wanted to see 3.5 number 7. So let's go back and go to that guy. All right. Yes, I realize I will get no points for that. So I just want to make sure you guys are seeing the assignment screen, not the whiteboard. All right, so let's go find that guy. All right, so 3.5, good old trig functions. Okay, so here's number 7. So this time we've got another function that we're trying to differentiate. We've got 2 sine of x over 1 plus cosine of x. And there are 2 things they want us to do here. They want us to find just the derivative itself, so the derivative function. That's what this first piece is saying, right? That just means what's the function derivative, or the derivative function, so in terms of x's. And then for the second part, they just want us to plug 4 into that derivative. Okay, so again, yours may look slightly different, but it should be fairly similar. So let me go back to the whiteboard here. We'll go ahead and clear this guy, and let's see what we can do. All right, so we'll start the same way. We've got our f of x is 2 sine over 1 plus cosine. So again, this suggests that we use the quotient rule, right? We've got one function being divided by another. And we can't pull that same kind of trick that we just pulled where we split it apart because there's addition on the bottom, so that doesn't really help. There might be a way to use some sort of an identity to change it, but I think that's probably going to be more work than just diving into the quotient rule. So how about we just do the quotient rule? So here's the function on top, 2 sine x, and on the bottom we've got 1 plus cosine of x. So we need their derivatives. So let's start with 2 sine. So the 2 is a constant multiple, so it just goes along. And then we need the derivative of sine. So what's the derivative of sine?
Cosine.
Good, that's cosine of x. All right, so we get 2 cosine of x is that derivative. Moving to the other piece, 1 plus cosine, well, the 1 goes to 0. And then the derivative of cosine is negative sine. Okay, so let's put those together. So we get f prime of x is equal to 2 cosine of x times 1 plus cosine of x minus 2 sine of x times negative sine of x, all divided by 1 plus cosine of x squared. So again, that's your quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by the bottom squared. Now this one I am going to simplify a little bit, just because I can. We're going to get 2 cosine of x plus 2 cosine squared plus 2 sine squared. Right, the negative makes it a plus. And now I'm going to make use of my identities. look at those two guys, the 2 cosine squared plus 2 sine squared. That's actually the same as 2. Because we can use the Pythagorean identity. So 2 cosine squared plus 2 sine squared is equal to 2. Now this one I can factor. Right, I can factor out that 2. And so notice that I've actually got common factors on top and bottom. The 1 plus cosine is going to cancel with one of those 1 plus cosines. And what I'm left with is just 2 over 1 plus cosine of x. All right, so this is what I would put into the first box when it says what's the derivative of 2 sine x over 1 plus cosine. So then for the last part, it says what's f prime of 4? Well, now all I'm going to do is plug 4 into this. So I get 2 over 1 plus cosine of 4. And that's as good as I can give you right now, unless I had a calculator, because 4 is not a nice angle. I don't know exactly what its cosine value it is, but I'm pretty sure that it's cosine, it's going to be a negative number, cosine of 4, but that's best I can tell you right now. So that's what I would put in my box, unless it said, I didn't actually pay enough attention to see what it said to put in there. You know how sometimes it'll say, be accurate up to 4 decimal places or something like that. If that's the case, then this isn't what I would put in. I would actually get a decimal number for it. But in general, leave it like this. Leave it as 2 over 1 plus cosine of 4, because that is the answer. As soon as you go to your calculator, even if you give me 1,000,000 digits, it's an approximate answer. And in the math world, we'd rather have exact numbers. If you're using this for something in, say, a science class, then yes, you'd want a decimal number, but we leave this as exact. All right, so any questions on this one? You're welcome, Elia. One thing that often gets asked at about this point in a problem like this, someone will say, okay, so I got this all set up using the quotient rule, but the distributing I wouldn't have seen using the identities and blah, blah, blah. And so a lot of times people ask me how far I want you to take it. If you're taking this on an exam, and I put this on here, let's say, so on the next exam you have something like that, really I'm just looking for, did you set up the quotient rule right? The rest of it is algebra, trig, that's not what I'm testing you on. So on an exam, if you just gotten to this first stage, I'd have called it good. I might have said something like it could simplify to here or something like that, but I'm still going to give you the points. However, we're also going to start using these things. And when we start using them, we're going to see that it's actually much more useful to do the algebra, depending upon what we're trying to do. So it's probably good to just get in the habit of doing the distribution and the simplifying. And with trig, always look for sine squared plus cosine squared. Always. It shows up a lot, and it's a great way to simplify, right? It was nice to be able to turn it just into a 2, which then ended up letting us go even further with the simplification. But regardless, I'd much rather have a 2 than a bunch of sine squareds and cosine squareds. All right, so there's that one. Okay, so unless there are any other questions, we'll go ahead and hop to the whiteboard, and we'll start doing some new stuff today. And when I say we're going to do new stuff, we're not really doing new stuff. We're still differentiating. We're just going to be developing a new rule, and we're going to be applying it slightly differently. So. All right, well then I'm going to go ahead and switch screens here, and I will see you guys at the whiteboard. All right. Okay, so here's where we are at this point. We now have rules for all kinds of differentiation. So let me just kind of remind you the big ones that we've done so far. All right, so we've got constant multiple rules. And it just says that if y is equal to c times f of x, then y prime is c times f prime of x. So we've already made use of this a lot, even today. Constant multiples just to go along for the ride. We just differentiate the other function and multiply. We also have adding and subtracting. So if we've got a function that's made up of two other ones that we're adding or subtracting, the derivative is just the sum or difference of those two derivatives. Again, we also made use of this when we differentiated polynomials, right? You just do each piece separately and then combine them up. So we've got add and subtract. We also have multiply, right? So this is the product rule. So if we've got two functions that are multiplied together, then the derivative is just given by this series of products, but we differentiate the first function, multiply it by the second, and then add to it the derivative of the second times the first. Right? So we have the product rule. And then we develop the quotient rule, which again is exactly what it sounds like. This time we've got division. And it actually starts very much like the product rule, right? Except on the top, there's actually a subtraction. And then we do end up with a fraction here. We end up with the g of x squared. Okay, so we've got all these rules so far. And this is awesome. This is great, but there's still one situation we haven't dealt with that we need to, and that is what happens when we've got composition. What about when we put one function inside of another? Okay, now I'm going to go ahead and tell you that this one, we call this the chain rule. That's the name for this. But the chain rule, again, this is when we're dealing with composition. So we need to develop that today. And then once we've got that, we're going to be able to use this stuff. We're going to see what good it is, why we care about them. All right. So let's build this. Let's figure out what the rule is for the chain rule for composition. And then I'll show you a bunch of examples. And this will allow us to start dealing with ones that are similar to what we already know how to deal with, but don't quite work out. Like you may remember there was a homework question that Aaliyah asked me last week. It was something like the square root of x plus 2, and it was all inside the square root. And unfortunately, we didn't have a rule for that. Well, this is going to take care of it. So we're going to be able to address things like that one in just a little bit. All right, so we're going to fill in what goes here, but we're going to prove it. We're going to develop it. And just like all the other ones, we're going to go back to the limit definition. So let's see how this plays out. So if I've got composition and I want to differentiate, I still want to do the exact same thing, right? So if I've got f of g of x, then y prime is going to be the limit as h goes to 0 of f of g of x plus h minus f of g of x divided by h, right? That's one form of the derivative. Remember, the idea is that we're putting in x plus h, subtracting the original, and then dividing by h, right? And just to make sure that you remember this other one, remember the other one would be the limit as x goes to c of f of g of x minus f of g of c divided by x minus c, right? So it was the two different forms. They both mean the same thing. Just the one we're saying make that gap drop to 0. The second one is saying bring those 2 points together. Same thing. Okay, so this is nothing new. This is, you've seen a million cases of this. But what we're going to do is we're going to take one of these guys and then we're going to run with it. Now, it turns out that the one we're going to use is actually the second one. Second one's easier in this case. So we're going to take this second one and we're going to see what this gives us. But this is another place where we need a miracle step. All right, so here's what I'm going to do. I'm going to take this fraction and I'm going to multiply the top and bottom by the same thing. So in essence, I'm multiplying by 1. But what I'm going to do is I'm going to multiply this by g of x minus g of c divided by g of x minus g of c. Okay, so hopefully you're good with it. I didn't change anything. I just multiplied it by 1. I just multiplied it by a special form of 1 because it's going to work out, right? So if you were to ask me, hey, Bruce, why did you pick that one to multiply by? I'm going to go, because it's what's going to make it work, hence the miracle step, right? The math gods smiled upon me and said, hey, use this. Okay, it wasn't the math gods, right? It was whoever developed this a couple hundred years ago. But when that happened, it was inspiration, right? But here's why this works out. Let me split this fraction apart. Since I've got multiplication, I can actually kind of move things around on top and bottom. And here's what I'm going to do. I'm going to write this as the limit as x goes to c of f of g of x minus f of g of c divided by g of x minus g of c times g of x minus g of c over x minus c. So really all I did was I took those two bottoms and I swapped them, right? But I can definitely do that because this is multiplication. The order of multiplication doesn't matter. And hopefully you remember when you have fractions, basically as long as stuff on top stays on the top, things on the bottom stay on the bottom, you're still fine. All right, so what? So what? Big deal. What does this do for us? Well, take a look at the second set here, this piece over here. Hopefully you notice that that's just the derivative of g. If you go back and you think about the forms for the derivative of g, as long as x is going towards c, which it is, this guy is just g prime of x. All right, well, let me just rewrite that then. That guy is just g prime. All right, now the first piece. Looking at this one, it may not be exactly clear what this is because it has some more stuff in it than what we're used to for the derivative. But this guy's also a derivative. Notice that it's a derivative of f. That's our outer function. We're just evaluating it at g. So there's function composition going on there. So what we've got is f prime of g. So by introducing that miracle step, by using that miracle step, I actually was able to create two different derivatives that are being multiplied together. And there you go. We just developed the chain rule. By doing it one time with generic functions, we now know how to differentiate any composition. All right, so this is what you want to put in your box for your y prime, or remember when I was making that list of all the different rules, this is what's going to go underneath it, but this is the chain rule. So what we're going to do, there's two pieces to this. The first is we need to differentiate the outside function. That's what f is. F is the outside function. So we're going to differentiate the outside function. And we're going to plug in the original interior function. But then we multiply by the derivative of the function that's on the inside. Now, I know when you see it written like this, for most of you, it's over your head. You're like, oh my God, I'm never going to understand this. This is super confusing. Yeah, in this form, it looks ugly, but I promise you, we do a couple of these, you'll totally understand what the process is. All right. So, but it's all about recognizing the function that's on the outside and the function that's on the inside. Okay, so I don't know if you remember this back in pre-calc days when we taught you about composition. That's one of the things we tried to reinforce, was how to recognize what's on the inside and what's on the outside. And today is the day for why we did that. Right? Don't you love learning all this stuff later? Like, oh, that's why we did that. It's just, we never would have gotten through pre-calc if we always referenced where you're going to use these things all the time. So, but anyway, let me show you. Let me show you how this works. It's really not that bad, and it can be a huge, huge, huge time saver. Okay, so let's do some examples. And I'll try really hard to not erase this so that we can always reference it, but at some point I probably will. So FYI. All right, so here's an example. Let's say we've got y equals the sine of x squared minus 4. Okay, so hopefully you see the composition. Am I correct there? Give me a thumbs up if you see the composition. By the way, I don't know if you know that you can do that on Zoom. There's a little thing where it says like reactions. Just give me a little thumbs up. Okay, so I'm seeing lots of thumbs up. Cool. So our outer function is sine, and our inner function is x squared minus 4. So in the context of how we wrote this before, we would say that f of x is sine of x, and g of x is x squared minus 4. Okay, so if you want to translate it to this kind of phrasing down here, that's what the different pieces are. Okay, so what we need to do is start by differentiating f. So f prime, that's cosine, right? The derivative of sine is cosine. So we needed f prime. We also need g prime. So let's just get that while we're here. The derivative of x squared minus 4. We're going to get 2x from our x squared. And then the minus 4 goes away. because it's just plain old 0. All right. So now let's put this together. So we're going to get y prime is equal to. So I need f prime, which was cosine of x, but I need to evaluate that at the original interior function. So all I'm doing, that x squared minus 4, instead of putting it into sine, I'm putting it into cosine. I'm putting it into the derivative. And then I multiply by g prime. Multiply by 2x. So there's your derivative. The derivative of sine of x squared minus 4 is 2x cosine of x squared minus 4. So we differentiated sine to get cosine, so it's still cosine of all that stuff. And then we multiply by the derivative of what's inside. So you'll hear me say that phrase all the time. I'll be like, okay, now let's multiply by the derivative of what's inside. We're doing chain rule. So Erez, you put in the chat box, you got the x plus 2x minus 2. That is the factoring of x squared minus 4. Turns out we don't need to worry about that here. It's not actually useful for us. You could split it apart like that and then do some things with cosines and, oh, sorry, that wasn't you, Erez. Oh, that was Fanray, my bad. But we could split it apart like that, but it's not necessary. All right, so there's your derivative of sine of x squared minus 4. So let's do another one. Let's try y equals the square root of x plus 4. So again, this is similar to the one that came up in a homework question last week. But now we don't have to use the limit definition. Now we can use the chain rule. So again, this is composition. Hopefully you see it. Right, thumbs up. We've got x plus 4 that's being put into the square root of x. So in the language of what we've been doing here, f of x would be the square root of x, and g of x would be x plus 4. All right, so x plus 4 is going into square root. All right, so let's use the chain rule. So we have to start by differentiating the outer function. The outer function is the square root of x, and to help you see what to do with that, remember that radicals can be written as exponents. They're just fractional exponents, so the square root of x is x to the 1/2. So now we can differentiate. So let's get the two derivatives again. So f prime of x is going to be 1/2 x to the minus 1/2, which is also known as 1 over 2 square roots of x. Okay, so that's the derivative of the outside. And then the derivative of the inside, x plus 4, its derivative is just 1. All right, so now we're ready to put this together to get our y prime. So y prime, using the chain rule, is going to be 1 over 2 square roots of x plus 4. So I'm taking the derivative of that outer function, but I'm putting in the x plus 4. Right? I'm still evaluating it at the original function. And then I need to multiply by the derivative of what's inside, which in this case is just 1. So we get y prime is equal to 1 over 2 square roots of x plus 4. So that's the derivative of the square root of x plus 4. So go back to that one, and I'm pretty sure that was you, Aaliyah, so you probably remember exactly the one I'm talking about. But go back to that one and go see what derivative we found once we did the whole limit definition. But then try it with chain rule. You'll see that you get exactly the same thing, just way faster. Because we already did that limit definition once. We're already there. Okay, so it's always differentiate the outside, then multiply by the derivative of what's inside. So let me show you one more example where this is super useful, like way faster than doing it other methods. Before I show you some quirky things with this. All right. So how about this guy? What if we had y equals 4x squared minus 1 to the 8th? And I want to find its derivative. So first of all, we don't have to use chain rule because we could distribute this out, right? We got this to the 8th. We could use the binomial expansion theorem, make this huge polynomial, and then just differentiate each of those pieces using power rule, right? So we don't have to use the chain rule, but the chain rule is going to be way faster because we don't have to do that, multiply everything out, right? So check this out. Do you see the composition again? Yeah, I'm getting some thumbs up. Cool. So we see the composition. It's 4x squared minus 1 to the 8th. So our outer function is x to the 8th. Our inner function is 4x squared minus 1. Okay, so you're probably getting tired of seeing me write these every time. I'm about done writing them. I think we're starting to recognize where we are in terms of what's the outside and the inside. But we go ahead and differentiate them. So x to the 8th, of course, is 8x to the 7th using the power rule. And then g prime of x is going to be 8x. Right? The 4 stays there. X squared gives me a 2x. So 4 times 2x is 8x. And then the minus 1 is a constant multiple, so it goes away. So here's our derivative then. Y prime is 8 times 4x squared minus 1 to the 7th. So I've got my 8x to the 7th, but I'm plugging in my original function. And then that's times 8x. So y prime here is 64x times 4x squared minus 1 to the 7th. So had you done the algebra originally and distributed it all and then done the power rule, that thing then would have actually factored to this. So think about that. One, we didn't have to do all that expanding out algebra. And then number two, we already have it now in factored form. Oh my God, like imagine we wanted to find out where this was 0, let's say. It's going to be so much easier to figure out where this is equal to 0 now because it's already factored. So this chain rule idea, it does actually help us a lot when it comes to algebra. It can save us lots of time. We just have to get comfortable with A, recognizing we've got composition, and then B, doing the process. All right, so how are we feeling about this? Not too bad, hopefully. All right, well, let me show you a couple more things about this. First is what if it's not just one composition? Like, what if it was this guy right here? So this time, let's go with y equals tangent squared of 3x cubed minus 2x. Okay, so yeah, it doesn't look terrible probably. Well, it doesn't look nice, but you can imagine functions that are way worse than this. But it turns out this has more than just one composition, right? Because here's how this plays out. That's squared. Remember that we put that squared there just for convenience, but what's really going on is we've got this whole tangent of stuff being squared. So if we were going to use the same language as before, where we say, okay, the outer function is f, the inner function is g, in this case, then the outer function is actually just x squared. Right? We're taking this whole tangent thing and we're squaring it. So the last thing that's happening is square. So that's our outer function. So our inner function is the tangent of 3x cubed minus 2x. And you can see that that's composition again. It's something that's getting plugged into the tangent. So this one's really composition of 3 functions. We're taking 3x cubed minus 2x, we're putting it into tangent, which then we're putting into x squared. All right, so then you might ask yourself, well, how do we deal with this? What changes? And the answer is nothing. Nothing changes. We still want to do this the same way. We want to start by differentiating the outside function and evaluating it at the inside function. Okay, so our y prime, it's going to start with a 2 times tangent of 3x cubed minus 2x. And that's coming from the fact that the derivative of f is 2x. All right, the derivative of x squared is 2x. So I've got 2 times what's on the inside. But now I need to multiply by the derivative of g. So I need to take this guy and I need to differentiate it. Well, that's going to require chain rule again. I've got tangent of stuff. So the derivative, I need the derivative of tangent. Well, the derivative of tangent was secant squared. So I'm going to get the secant squared of the stuff. And then I need to multiply by the derivative of what's inside that one. Well, the derivative of what's inside there is 9x squared minus 2. So if I put that all together, here's our y prime. So y prime is 2 tangents of 3x cubed minus 2x times secant squared 3x cubed minus 2x times 9x squared minus 2. And you literally can see all of the derivatives. Let me put little spacers here so you can see where they all happened. The derivative of squared, something squared, is 2 times that thing. The derivative of tangent is secant squared. The derivative of 3x cubed minus 2x, 9x squared minus 2. So if you have more than one composition, just keep applying the chain rule. This is chain rule inside of the chain rule. If we had yet another composition, it would be chain rule inside chain rule inside chain rule. and so on and so forth. So you could have as many of these as you can imagine by creating a function that has lots of composition. All right, so I know it's easy for me to say, you just keep doing chain rule, no big deal. But it's really easy to get lost in there, right? Well, let me show you another way that we can look at this that might be a little bit easier when it comes to multiple compositions. And I think it also helps you see the name chain rule. This is actually where you can start seeing why it's called the chain rule, because you have a chain of derivatives that are all being multiplied together, right? So that's actually how it got its name. It's the chain of derivatives. Okay, well, let me show you another way of doing this that I find a little bit easier, at least in terms of making sure I'm not missing any pieces. And it actually makes use of the other notation for derivatives, right? This one we've been using the primes, the Newton notation. Let me show you how we can approach this with the Leibniz notation. Leibniz, that was the dy dx, the one that makes you think slope. So let me actually just come back to this one real quick, the y equals 4x squared minus 1, and that all being raised to the 8th. So here's how I think about this. 4x squared minus 1 to the 8th, I don't know how to differentiate. I mean, I got the chain rule, but just in terms of our other rules, I don't really know how to differentiate it. Now, what if instead it was fist to the 8th, hand to the 8th, u to the 8th? Right? If it was just one variable raised to the 8th, I know exactly how to do that. So what if, like I've got right here, I rewrite this as u to the 8th. I'm just going to write on the side here, though, that I know that u was 4x squared minus 1. Right? If I just allowed that 4x squared minus 1, if I just renamed it, I called it u, then this looks like u to the 8th, and I know how to differentiate that. Easy, super easy. And if I look at u, I know exactly how to differentiate u, 4x squared minus 1. That's no big deal. So here's how I'm going to build my chain for my derivative. The derivative I want is dy dx. Right? I want slope, dy dx. Changing y over changing x, y prime. So I want dy dx. Now, the problem is I don't know y in terms of x anymore. Y, I've written in terms of the variable u. So I'm going to put here dy du. Because if you look just above here, y is in terms of the variable u. Okay, well that's great, but I need to get rid of a du. So since these are fractions, I'm going to multiply by another fraction that has a du on top, right? Because the du's are going to cancel. So now I come over and I look at u, and u is only in terms of that variable x. So I can get a du dx. But these are the links in my chain. This is the derivative of the outer function. This is the derivative of the inner function. And now that I've built that chain, I can do these derivatives. This is 8u squared, or sorry, 8u to the 7th times 8x. And now I just plug back in that u. I knew my u was 4x minus 1, or sorry, 4x squared minus 1. So I go ahead and put that in, and you'll notice that this is exactly what we found for the derivative. So by using these substitutions, these letter substitutions, it can make it a little bit easier to spot what the chains are, what the derivatives we need are, and we can get to our answer a little bit faster. Now, I don't normally do this if it's just one composition, like with this guy. Since it's just one composition, I differentiate the outside, multiply by the derivative of the inside. Where I really use this is when we get things like this second one, where it's easy to lose track of where you are. So let me show you this process with that second example. and we'll see that we get the exact same derivative. It's just maybe not as confusing. It might be a little more straightforward. So let's come back over here, and let me show you how this is going to work. So I'm going to start with just some substitutions, because I don't want all this, like, it's too complicated, right? So here are some substitutions. I'm going to start with, what if I let u equal 3x cubed minus 2x? If I do that, then this y equals, now looks like y equals tangent squared u. Now, tangent squared u is not quite good enough for me to differentiate, because I don't have a rule for that. So I need to do another substitution. So let me call this one, say, t. So we'll let t equal, no, it was w, we'll call it w, tangent of u. So if I let w equal tangent of u, then this guy looks like w squared. And now I know how to differentiate w squared. Easy. That's a power rule. Let's go back and check our other letters and our other substitutions. So for w, I've got tangent of u. Well, I know how to differentiate tangent. That's one we developed last week. Derivative tangent of secant squared, so no problem. And then if I look at u is 3x cubed minus 2x. Again, please, all day, I'll do polynomial. So those three pieces are all such that I can differentiate. So now I'm ready to build my chain. So here comes my chain. It's going to be, I want dy dx, so I need to start with y. Y now is in terms of w, so I'm going to have dy dw. My next piece then needs a w on top, so let's go look at w. And w is only in terms of u, so we'll have dw du. Which then means, of course, we go to du. And u is only in terms of x. So this one's going to have three pieces. dy dw times dw du times du dx. So three links in this chain. But now I'll get those derivatives. So dy du, or sorry, dy dw is 2w. dw du, the derivative of tangent, is secant squared of u. And then times du dx. Well, that's my 9x squared minus 2. And now all that's left is to plug back in all those places where I put in the variables. Okay, well, I have 2w. W was the tangent of u. So I'll go ahead and just write that as tangent of u for right now. Times secant squared u times 9x squared minus 2. All right, so I took care of the w. Now I need to take care of the u's. Well, the u, that was 3x cubed minus 2x. And notice that that's just this next line. Right? I put those in for my u's. So we get to exactly the same place. You can still see the three pieces. It's just this time we didn't really have to worry about what's inside of what's inside of what's inside of what, like trying to keep track like that. Instead, by writing it out as those letters equal, that's how I kept track of what was inside. So I'm a huge fan of using this Leibniz notation, especially when I've got lots of composition. If I've only got like one composition, I've got one composition, no big deal. But when I've got lots of it, and it's easy to get confused where you are and have I taken care of this piece or that piece, this can definitely help you. Once you get it down, it's no big deal. You can have like 20 compositions, you know exactly how to do it. Just work outside in. outermost function, differentiate. Go to the next one in, differentiate. Next one in, differentiate. Keep going until you're done. But that comes with practice. So this can help you get to the point where once you've done enough of them, you start seeing that and speed it up. But just another approach. If you don't like it, that's also cool. You don't have to, right? Just things I like to share with you as ways of trying to remember the process. All right, so good for that one? Ish. So chain rule allows us to take care of composition, which means we're good. We're ready. We can now dive in and start using derivatives for what they're intended. All right, so any other questions before we kind of move on to the next stage? No? Okay, well then what I'm going to do is I'm actually going to backtrack. So you remember I told you we skipped a section. I think it was like section 3.4 or something like that. We're going to go back and talk about that now. I wanted to get these other rules in. 3.4 really talks at what we care about, what the derivatives. I just wanted more rules before we got there. I want to be able to do more. So we now can differentiate pretty much everything with the exception of just random functions that we come across as we go along, right? But you're going to see that there is a derivative for e to the x, and there's a derivative for natural log, and insert your favorite functions. But these bigger rules, the power rule, the product rule, the quotient rule, the chain rule, like they all apply no matter what our function is. Okay, so why do we care about derivatives? Let's talk a little bit about that with our remaining time today. Okay, so uses of derivatives. So the first thing I'm going to tell you about this list is that this list is incredibly long. We're going to keep adding to this list as the quarter goes on. You'll actually keep adding to this list the more you take calculus. Because what do we use derivatives for? Tons of things, okay? So this is by no means complete. We're not gonna do, I mean, even for this quarter, I'm not giving you everything that's gonna be on this list, but we're gonna at least start it out. Okay, so some uses of derivatives. First and foremost, this was the actual context of where it came from, was rates of change. If you want to know how something is changing, that's what we use the derivative for, right? So I put here rates of change, and I'm actually going to put in parentheses here, instantaneous. So we know exactly how something is changing at that moment, all right? Or at that one point, instead of getting an average over a certain interval, we're finding it instantaneously. Okay, but we've already talked about this, right? This is the whole secant line approximation stuff, but I don't want to go more into it. I just want to put this on the list because we've seen that that's one of the things that we use it for, and it was the reason that it was created, right? Okay, so a second thing that we use it for is for slopes of tangent lines. So there's another one you already know. If you want to know the slope of a line that's tangent to a curve, you can take the derivative and that will tell it to you. Okay, so another one that we're not going to really go into, but wanted to put it on the list. But we also knew that those were kind of related to each other, so good. All right. Now, the next one is another one that we've also talked about, but I want to talk a little bit more about it. And that is to figure out the velocity of an object. I should probably put here, find velocity of an object. Now, velocity is a specific rate of change. It's a change of position. in terms of time. But it's such an important topic that it kind of gets its own line here, right? Rates of change is really like a broad general topic, but this allows us to be or go a little more in depth in this one very specific thing. So kind of how this plays out is that suppose that the position of an object is given by a function. And it's going to be, say, f of t. And t here, whenever we're talking about the position with t, t is reserved to be time. So if you ever see me write time, or t, in this context, I'm definitely talking about time, how much time has gone by. All right, so then velocity is going to be the derivative of this function with respect to time. Because velocity, the units of it, meters per second, feet per second, miles per hour, it's always a distance per time. And so we want to differentiate with respect to time. So we, of course, also know that as f prime of t. So if you can ever describe the position of an object in terms of time, if you differentiate that, you'll get its velocity. But related to velocity, and I think I kind of have beaten around the bush with this a bit. I don't know if we've really talked about it. So I'm going to call this, say, 3b, is the acceleration. And acceleration is how velocity changes. So it's another rate of change. It's just a rate of change in velocity. So acceleration it's the derivative of velocity with respect to time, which means it's the derivative of a derivative. So it's actually the second derivative of position. I think I can avoid the glare a little bit better if I'm over here. All right, so check it out. You start with a position f, you differentiate it once, you get velocity. So velocity is f prime. If you take the second derivative, you get acceleration. And for those of you who have taken your physics, you see why this is a big deal. For those of you who haven't taken physics yet, you'll see why this is a big deal. Because everything in classical mechanics, talking about how objects move, come down to finding velocities and accelerations and positions and their interrelationship. And it turns out it's just differentiation. That's it. Okay, so I want to show you an example. It means I'm going to have to kind of erase my list, but we'll remember where we are. We're going to be starting on number 4 with something new. But let me give you a position of an object, and we'll talk about velocity and acceleration and all that good stuff. All right, so let me just start by giving you this. Let's say that we've got a position function. And again, it's going to be for an object of some type, doesn't really matter. But let's just say that it's given by y equals minus 4.9 t squared plus 12t plus 3.5. So we've got some object that's moving. And we'll even let y be y. Let's say that this is a vertical like we're used to. So the vertical position of this object is given by this formula. So here's what we're going to do. We're going to find its velocity. We're going to find its acceleration. And then we're going to play around a little bit with them and see some interrelationships between these functions. Okay, so first let's find the velocity. Okay, so A, let's find the velocity. All right, so V is equal to Y prime. So this is just a polynomial, so we can use power rule. So we get a negative 4.9 times 2t, right? Minus 4.9 is a constant multiple, t squared gives us a 2t. 12t, its derivative is 12. 12 goes along, derivative of t is 1. And then the 3.5, well, it goes away, it goes to 0. So we get y prime is equal to negative 9.8t plus 12. All right, so this is the velocity of the object at any given time. All right, so plug in t equal 1 after 1 second. We know that its velocity is 2.2. The 2.2, it's meters, so meters per second. We might go, okay, well, what about at t equal 10? Well, if we plug in 10, we get negative 98 plus 12, which would be negative 86. So that would have a negative velocity of 86 meters per second. Okay, now, negative velocity, don't let that freak you out. I know that I mentioned this before. You can have negative velocities. It just is talking about its direction of travel. So when we've got a positive velocity, we're going upward because we're having a positive change in our y value. When we have negative velocity, we're going down. Our y values are getting negative. So at t equal 10, 10 seconds from now, this thing is going downward. That's what I can tell you by knowing that it was negative 90 or 86 or whatever it was. At time t equal 1, remember this was a positive number, 2.2. That means after 1 second of this thing moving, it's moving upward. Right, so that's how you would interpret that. Okay, well, there's our velocity. So then here for part B, let's find the acceleration. So acceleration is y double prime. So that just means we want to differentiate y prime. Well, let's use the fact that this is a line to help us out. So the slope of the line is the derivative. So we get negative 9.8. So this is constant acceleration, always acceleration. And it means that the velocity is always decreasing since it's negative, right? The change in this velocity is negative. All right, well, this example, what this actually is, because the acceleration is always 9.8 pointing down, some of you may recognize that. This is gravity, at least on Earth, and at least over short distances, it doesn't change, right? It's around negative 9.8. And so this is what we call free fall or projectile motion. But this is an example of something that's only going through acceleration due to gravity, being pulled down. You've seen this before, I'm sure, many different places. And in fact, where it comes from is using calculus, just going backwards, starting with this and going, oh, what function gives us a derivative of negative 9.8? Well, it's this line. What function gives us a derivative that's this line? Oh, well, it's this quadratic, right? So we're really just going backwards. But if you're given a position, you can find your velocity and acceleration this easily. Now, I do want to point out a couple more things that are kind of interest. Okay. how about this one? Look at the velocity. Where is velocity equal to 0? So let's answer that. This is going to be part C, I guess, of my question. All right, so when is the velocity of this thing actually equal to 0? So at what point does it momentarily stop moving? Well, all we got to do is take our velocity function and set it equal to 0. So we've got negative 9.8t plus 12 equals 0. So t is equal to 12 over 9.8, which is whatever that decimal is. I don't really care at this moment. It's 1 point something. But that's going to be when we're actually at velocity 0. Now, if we were to look at a graph of this, so if we go back and we actually draw a graph of this quadratic, what you're going to see is something that looks like this. So it's a sad parabola because of the negative a. It's got a y-intercept of 3.5. Right, so it's going to do whatever. It's going to be like that. Now, in terms of our specific problem, we don't care about this piece over here in the negative. But this is what it looks like going further. Okay, so let's think about what it means for the derivative to equal 0. And let's think about it as tangent lines. Let's go back to number 2 on our list. Kind of think about that. So what does it mean if the slope of the tangent line is 0? What kind of lines have a slope of 0?
Constant.
So constant functions or horizontal lines, right? Horizontal lines, constant ones, those have slope of 0. So thinking about this graph of a parabola, where do we have a horizontal tangent line? Well, that happens when we're up here at the top, when we're at the vertex. So at this point, if you were to actually look at tangent line, it would be a horizontal tangent line. All right, well, that's where this t value is. This guy, the 12 over 9.8. Again, it's some decimal number, but that's going to be the same place. All right, so in essence, when I ask where is the velocity equal to 0, it's the same question as where is the vertex. So go back to pre-calc. And I don't know if you remember the fast way of finding the x-coordinate of the vertex. It was x equals negative b over 2a. So let's translate to this problem. So instead of x, it's t, but let's put in our numbers, b and a. So b was 12, a was negative 4.9. And we get 12 over 9.8, which is that same place. So notice that calculus is actually giving us the same answers as algebra, which is a good thing. You never want to be in a place where calculus and algebra are giving you different answers, because then something's wrong. All right, but check this out. You were told that formula, negative b over 2a, and you were just kind of told, you just kind of went, okay, cool, it works. And check this out. It comes from calculus. Because think about what we just did. We looked at a derivative, and we saw where is equals 0. Well, let me make this a generic quadratic. And let's watch what happens when we differentiate and then set equals 0. So if I've got y equals ax squared plus bx plus c, y prime is going to be 2ax plus b. So we're just using power rule, right? X squared gives me 2x, the a stayed along. bx gives me b, and then c goes away. Well, if we take 2ax plus b, and we set it equal to 0, and I solve that for x, check it out. We get x equals negative b over 2a. Yeah, so whoever gave you that formula, it was probably someone like me. Whoever gave you that formula at some point, they did a little calculus. They just didn't tell you. That's where that comes from. That's why we have that shortcut for finding the vertex of a parabola. Well, there are other ways you can get there, but this is the fastest and easiest way, is by using calculus. All right, so if you were given any function, any position function, you can find velocity by differentiating, acceleration by differentiating again. Just remember that positive velocity means you're moving in a positive direction. Negative velocity means you're moving in a negative direction. That's the only difference between plus and minus, is direction. Okay, so there's a, well, we've already kind of talked about that as a use of derivatives. Now you can see a little bit stronger why it's used. Okay, so let me add to the list now. Hold on one second here, guys. My phone just told me it was about out of power, and that's because it wasn't actually plugged in. So hopefully the screen doesn't go away. If it does, we'll deal with it. But let's add one more thing to our list here. Another use of the derivative. So this is going to be number 4 on our list. And this is going to be to approximate the function. We can actually use the derivative of a function to help us approximate the function itself. So let me kind of give you an example of what I mean. All right. So suppose I were to ask you, what's the square root of 5? And no calculators, no technology. Because I know you just,
5 to 1/2. Wait.
Okay, so it'd be the same as 5 to the 1/2, but I mean, like, what is this as a number approximation?
It's a decimal point.
Yeah, it is. What is it?
I can't say it. 2 points. It's 2 point something. I know that.
Okay, I'll definitely take that, Susanna. It's 2 point something. Right? We know it's 2 point something because 2 squared is 4, 3 squared is 9, 5 is somewhere between 4 and 9, right? So we know it's 2 point something. But again, I don't want you, no calculators, no punching it in, no pulling up an app on your phone, no going to the computer, anything like that. If we wanted to actually calculate the square root of 5, that's kind of difficult. I mean, we could do it the old-fashioned way, where you go, okay, I know it's a little bit bigger than 2, so let's try like 2.5, right? So you'd go, let's see, 2.5 times 2.5, that's 6.25. Okay, well, that's too big, so I got to bring it down a little bit, right? So you go, well, let's try like 2.3. So you take 2.3 times 2.3, and you get 5.29, I think. And you go, okay, well, wait, no, that's still too big. So then we go down to 2.2, right? And then we got 4.84. And you go, oh, okay, so it's somewhere between 2.2 and 2.3. And we keep refining and going until we get closer and closer and closer, right? So there's the old-fashioned way, using the intermediate value theorem, by the way. All right, anyway, so we could do this. That's kind of a pain in the ass, right? Okay, well, let me show you how we could use calculus to do this. So think about what we got. We got the square root of 5. Let's think about the square root function. So the square root function, as we all know, looks something like this. And somewhere out here is 5. And so I want to know this y value, right? This is the square root of 5. Now, square root of 5 is not a nice number, but there is a nice number close to that. Like I could come over here to 4. And what I know over here is that this is equal to the square root of 4, which is 2. So it's going to be slightly more than 2. Well, here's where the derivative comes in. Think about the derivative at 4. That's going to give me a tangent line, right? So this is the one that's got the line whose slope is f prime of 4. And if I were to follow that line over to 5, I'll put a black dot right here on the line. Notice that that dot on the line is actually really close to the dot on the curve. So if I just find the one on the line, that's going to be a really good approximation for the actual value. And finding the other point on the line is easy, because if I know the slope, like think about being on that line, right? I know that the slope is the change in y over the change in x. So my change in y is equal to m times the change in x. And my change in x is just how far I'm stepping over here. And in this case, it's going to be 1. So it's actually really easy to calculate how much I go up. I just have to take that horizontal step times my slope. All right, well, let me show you then how this plays out. So we've got the square root of x, also known as x to the 1/2. That's our function. I need to differentiate it. So if I use the power rule, I get 1/2 x to the minus 1/2, which is also known as 1 over 2 square roots of x. Now, what I need is the slope of this line, so I need to plug in 4. So f prime of 4 is 1 over 2 square roots of 4, which is 1/4. So that change in y then is going to equal 1/4, that was the slope of the tangent line, times 1, because I'm stepping over 1. Okay, so that tells me that my change in y is equal to 1/4. Now, that's not actually the change along the function, but it's a change on the line, which means this second black dot, that actually has a y value of 2.25. Because it was the original 2 plus my quarter. And so what I can tell you is that that square root of 5 is around 2.25. That's not an exact answer, but it's going to be close. And I know it's going to be close because I'm using that tangent line to approximate it. And that tangent line is a very good approximation for the curve at the point 4. And since I'm not going very far away, I know this is a decent approximation. Okay, so if anybody's got a calculator handy, get me what your calculator tells you the square root of 5 is.
It's 2.236, and some more numbers after that. But
Okay, cool. So from the calculator, it's 2.236 ... All right, so how do we do with our approximation?
Pretty good.
Yeah, it's not bad, right? 2.25 compared to 2.236. I'm off by if we just rounded it off here, I'm off by 0.014, slightly more than 1/100th off. I'm feeling pretty good, right? Now, what would make it an even better approximation is if that delta x was smaller, right? If it was a smaller horizontal step, then this line would look more like the curve and it'd be an even better approximation. So this is actually way better for something like, what if we want to know the square root of 4.1? Well, we could do exactly the same thing, except instead of a 1 here, it'd be a 0.1. We'd get a number 2.025, and if you saw what the square root of 4.1 was, you'd see it's a lot closer. Our guess would be a lot closer. But we can get really good guesses using the derivative. So we're basically using the derivative to create a line, using that line to approximate the curve. And it's a lot easier to move along a line and calculate than it is on curves. So here's another big use of the derivative is approximating function. Now, when you look in section, whatever it was, 3.4, you'll see other things they talk about. Marginal cost. That's a specific thing to business. They'll talk about population rates of change. Okay, well, there's an application directly to biology. I mean, and there are tons of these. I could spend all day doing examples from just about every field. But when you look at that and you run into those things, here's what I want you to do. I don't want you to go, marginal cost, I've never heard of it. What the? Don't do that. Look at marginal cost and see what is it saying. Oh, marginal cost is a rate of change in cost with number of items produced, right? Then have that go, ooh, rate of change. I know what that means. That means a derivative, right? So don't let the specifics throw you. Don't go, this business, I've never done that. Biology, I'm not a biologist. I don't know what they're talking about. Analyze it with the lens of calculus. Rates of change. What rate of change am I finding? That tells you where the derivative comes into play. Okay, so just always keep that in mind when we're doing these. Think, what is the rate of change? Because that's going to tell me what to do with the calculus. All right, well, I think we're out of time. Oh yeah, I'll look at that right on the nose. Anyway, so now we've got all the rules. We're starting to see where we use them. Well, next time we're going to continue. We're just going to keep going. We're actually going to look at how inverse functions are related to each other. Their derivatives are related to each other, which then is going to open the door for things like e to the x, natural log. So we'll kind of take care of all those details. So at the end of this week, we should be completely done with how to do derivatives. And then we'll keep marching in this, what do we use derivatives for, right? That's kind of the whole point is, now that we've got these tools, let's use them. All right. So with that, I'm going to go ahead and stop our recording and we'll call it a day.